Thank you to the organizers for giving me this opportunity to talk. So as you see, the title is Hadronization of the QGP as a Quench. And at the outset, I will apologize. We have been thinking about this problem since very recently. So it's still work in progress. But I mean, I hope all of you are able to take something valuable out of how we are trying to think about this problem. Okay, so I'll start. So as most of you already know, the QGP is actually an exotic state of matter formed in AA or PA HICs. And it's like a hot soup of quarks and gluons. And once formed, it expands and cools. And eventually, it evaporates into colorless objects, which are hadrons, which is what we see in our detectors. So this hadronization is basically this process of packaging these colored degrees of freedom in this soup into colorless hadrons in the final states. Now, what is the aim? So the aim is that in a very simple toy model, I mean, it's not even QCD, it's field theory, but in a very simple toy model, we basically want to develop something, some simple formalism, and actually calculate heavy flavor meson number distributions in the final state, given the initial number distributions of its constituent heavy and light quarks in the pre-hadronization phase. So I have put it in single inverted commas because it's a very simple toy model. I mean, it's not QCD, etc., but that's why I have just put it in single inverted commas. Now, why do we want to do something like this? It's that these HF meson yields are known experimentally. And if we are able to calculate such a formula, which I think we would be able to do in some time, we may actually deduce the distributions of the heavy and light quarks in the pre-hadronization phase. So such a formula can actually help us, or it can serve as a probe into the QGP in this toy model. And also it may provide insights into already existing hadronization models like instantaneous coalescence and fragmentation. So this is a nice review, which I think you all may know already. So what is the toy model? So in the pre-hadronization phase, which is the left of this diagram, what I have is a fundamentally UN colored complex scalar field, which I call chi. So I've drawn it big because it's like its mass it's like a heavy quark, so it's big. And it's immersed in this bath of another fundamentally UN colored complex scalar field, small phi. And there are no gluons. It's a very simple model. So this is like a toy for a QGP. And then what you do is that this hadronizes, okay, and then goes into these colorless mesons. So post-hadronization phase is just a single colorless scalar field. So pre-hadronization, the Hilbert space only has chi and phi Fock states in it. But post-hadronization, the Fock state only has these xi complex scalar states. So this hadronization, we are modeling by this object called Q. And what this Q is, I'll just say, in the later slides, I'll tell you what this Q is, but this is what we call a quench. So our title was Hadronization as a Quench. So this Q is our central object, which actually implements this shift. So it takes you from this Hilbert space to this Hilbert space. Now, within this toy model, I mean, the scalar field model, the aim is to calculate correlators between the number distributions of the HF meson xi and the light heavy quarks in the pre-hadronization phase, which are phi and chi. So computing correlators, something like this. And this correlator actually has a Q in it to just tell us that this Q is implementing the hadronization. And then convoluting the C with any given number distributions in the pre-hadronization phase, we can actually get what we want, these meson number distributions in the final state. So this function C, you may recognize, it's exactly like the recombination probabilities which are used in hadronization models. For example, in instantaneous coalescence, this C is just the Wigner distribution of the meson. Okay, now let me come to the central object, the main actor in this whole project. It's this quench Q. So the quench Q is actually implemented as a super operator, which means it takes an operator as input and gives back another operator. So it's designed to take in the pre-hadronization density matrix and give us the post-hadronization density matrix, which involves only xi. So it instantaneously takes this pre-hadronization thing into post-hadronization. So it's like an instantaneous hadronization. Now Q The super operator actually has been explored a lot in open quantum system literature. Actually, it's a special limit of what is called quantum collision models. So this is a any question was okay. So this is a nice review which actually gives you something about quantum collision models. So a special limit of these models is this super operator, something like this. Now in our context, this Q can be thought of in two ways. It can be thought of as an open effective field theory, and second, it can be thought of as a generalization of the S matrix. So let me say how. So Quench can be thought of as an open EFT. So it can be thought of as the effect which is induced by integrating out all the complicated environment which surrounds these phis and chis in the pre-hadronization phase. For example, gluons, photons, leptons, etc. If you integrate out that, then Q is the effective object which you get, which we are modeling here as a super operator. So these effects can be accounted for. I mean, all these environmental effects can be accounted for by systematically adding couplings between these final state mesons and initial state light quarks and heavy quarks. So this is exactly like how we do EFT in usual QFT, but this is like developing an open EFT for modeling this hadronization, which is modeled by a quench. Now, how about its relation with the S matrix? So we say that the quench is like a generalization of the S matrix. So it's a generalization of the S matrix for open systems. Now, S matrix, as most of us know, is that asymptotically free states come in, they interact in a complicated way at an instant, and then go away as asymptotically free states again. However, the S matrix is unitary, which means that it always takes pure states to pure states. I mean, it preserves the purity of states. But the quench 2 here, it also converts in states to out states, but it can also describe non-unitary processes like dissipation, etc. I think, I mean, it can take pure states to mixed states. So it can convert pure states to mixed states or mixed states to other mixed states. So this is how it's kind of a generalization of the S matrix. Now, let us come to the calculation we are doing. So the main object which we are trying to calculate is this Schwinger-Keldysh generating functional, which Loga was talking about in his lectures, but it's a bit of a modified Schwinger-Keldysh generating functional because you have a quench insertion in between. So let me explain. Let me unpackage this expression. So it's a trace. Now, this curly brackets, within this curly brackets, you have this pre-hadronization phase, which basically represents the evolution of the light quark and heavy quark density matrix, this initial state in the pre-hadronization phase. It's sourced by these J-phis and J-chis. That's how generating functionals work. You always source them. And then this quench implements the instantaneous hadronization. And after that has happened, the hadronized state actually evolves, which is a state with only the meson xi. And then we finally take the trace. Now, to compute this, we would certainly need a model for modeling this super operator Q, which is like modeling the hadronization. In this very simple model. So we kind of take a EFT-inspired model that in this super operator, we add all possible terms up to a certain degree consistent with symmetries dictated by the problem. This is how we usually do EFT. So that is what we'll do the same thing now with now on Q. So first of all, a little technical detail is that this calculation is best done in the coherent basis of the fields. So coherent states of the simple harmonic oscillator are just eigenstates of the annihilation operator. Similarly for fields, I mean, fields are also made of annihilation and creation operators. So they also have their coherent states. So this calculation is best done in the coherent basis. And in that basis, this quench actually has this functional dependence. So for example, phi is like a coherent state of the light quark. Phi tilde is like a coherent state of the light anti-quark. Chi is like a coherent state of the heavy quark, and this is like a coherent state of the heavy anti-quark. So we call this the quench kernel, and we will be operating, we will be working with this mainly in this thing to model this particular kernel. So to start, we impose a couple of reasonable demands. So first is like hermiticity preservation. These are just very general demands we can impose. So the thing is that given a Hermitian density matrix is input, so density matrices are always Hermitian because probabilities are always real. So it should take it to another Hermitian density matrix. So that actually translates, for this kernel, it translates to this particular demand that you conjugate it while also interchanging the R and L degrees of freedom. Okay, so this will be used in a small explanation later. That's why I'm introducing it, writing this down here. And the second reasonable thing which we can demand is trace preservation, that it should preserve the trace of the density matrix. This is basically the statement of conservation of probability. Oh, so R and L. So Schwinger-Keldysh contour has these two branches. So for example, here IR represents, I means that it's pre-hadronization. So there's only phi and chi. And in pre-hadronization, you have a forward evolution in time and backward. So whatever is on the forward, it's denoted R. And whatever is on the backward, it's denoted L. So R and L is the usual doubling which happens in Schwinger-Keldysh formalism, because there's a U and there's a U dagger also. So, and in the final state, you only have xis, because that is what our model is. Yes. Okay, so now we impose certain symmetries. So we are doing the usual effective field theory kind of thing for this Quench kernel. So we impose symmetries. So first we kind of impose U and color symmetry. So these, I mean, one subtle point is that we are imposing global U and color. I mean, that is because if we kind of introduce local, if we gauge this U and color, then we'll introduce gluons into the problem, which we don't want to do right now. So it's just global UN. And what we do is that under fundamental UN rotations, these are how the coherent variables transform. So we want to implement these symmetries on this particular kernel to kind of constrain the terms we kind of write down. And then we impose U1 heavy flavor, which is like invariance under U1 rotations of this heavy quark. And then we also want to impose U1 light flavor so that it's, it's invariant under U1 rotations of the light quark. If we kind of, the more symmetries we implement, it constrains our terms more, so it gives more analytical handle. So that's why we are, but these three are kind of what we impose. And you see that here the meson transforms in exactly the same way as chi, and here it transforms in an opposite way, because here we are thinking of xi as being made up of like something like phi star chi. So it's an anti-quark phi and a heavy quark chi. So that's why the sign difference. Now, let us write down the simplest, at the simplest level, which is the quadratic level. By quadratic level, I mean quadratic in these coherent variables. So as I showed, it has to depend on these. And if you see at the quadratic level, it's depending on these, which, so it depends on these coherent variables. So this expression actually tells you, it unpackages that particular expression for the kernel. So at the simplest level, lowest level, this is how the Quench kernel looks like. So this is, I have suppressed the color indices. And, oh, yes. So for a clearer understanding to, present it, for the moment, we kind of consider even a simpler model where we have degraded the fields to oscillators. I mean, that's the simplest you can go. But for the purpose of explanation, that is, good. So in this, you have the quadratic Quench kernel looks like this. So which kind of obeys all these symmetries, and also it obeys hermiticity preservation and trace preservation. Now, hermiticity preservation is basically tells us that this normalization and these lambda xi, lambda tilde xi, these are real numbers. And also it tells us that if here you have a sigma xi, here you must have a sigma xi star. So that is the demand of hermiticity preservation. And trace preservation gives us this simple condition that these four couplings are just unity. I mean, they can't be anything but one. And trace preservation also tells us that NQ has to have this particular relation with these couplings. Okay, now we add cubic couplings. So at the cubic level, what happens is that it looks like exponential of some polynomial, cubic polynomial in these coherent variables. And the terms in Q3 are basically these, which we add. For example, the unitary couplings are only two. Okay, why do I call them unitary couplings? It's because they only couple the RRR or the LLL. So there's no LLL here, but it's purely RRR. That's why I call it unitary. I mean, this is something which I can explain if someone asks that why pure R or pure L couplings are unitary, whereas mixed R and L are non-unitary. But let me not go into that right now. So, I mean, unitary couplings are only 2 and non-unitary couplings are like 6. These are the only terms which we get after imposing these symmetries and so on. And here HC basically means that you kind of complex conjugate while also interchanging R with L. Okay. Okay. So these are the cubic couplings, all the cubic couplings. And we finally want to do Feynman diagrams. So I mean, how do these cubic couplings look like? So for example, a unitary vertex will look like this, which is the first one here. It's like xi star fr, phi CIR, chi IR. So it looks like this. So this means that an anti-quark and a heavy quark, the quench connects them with G to this anti-meson in the final state. And RRR means that only the ket degrees of freedom are connected. But something like this, for example, the non-unitary vertex, it has some L also being connected. L means that it's connecting the bra part of phi star with the ket part of chi, giving you a ket part of xi. So here, bras and kets are different degrees of freedom in the Schwinger-Keldysh formalism. So everyone has their own propagators and so on. So these are some couplings which we have, cubic couplings. Now, we should also impose trace preservation on these couplings according to what we are doing. So the trace preservation actually gives us some relations between all these different couplings, which are like 6 complex equations and 4 real equations. So this is in the simpler complex SHO model because that's easier to explain. But what happens in field theory is that all these couplings, lambda, xi, g, they start depending on 3 momenta. And also these, everything starts depending on 3 momenta here. And you also get convolutions with 3 momentum space if you do it in the field theory. So now I'll just say what is ongoing. I mean, we have recently started, so there's not many results to show, but I mean, we are just doing a calculation like this. But so what we are doing is that we are calculating the Schwinger-Keldysh generating functional, this trace, and we are doing it perturbatively in these different couplings, these couplings which I showed, G, GC, H, HC, kappa, kappa, C, Y, YC. And the future is that to relate this very simple toy model to other hadronization processes like instantaneous coalescence and fragmentation, and of course, refine this model towards actual QCD, I think. And then another interesting future aim could be like bootstrapping the quench. I mean, can we reconstruct these? I mean, it's like an inverse problem that can we reconstruct these quench couplings from the recombination probabilities C? If we can do that, then that would be another way to kind of probe this QGP in this simple model or in the refined version of this model. And actually, aside in another work which has been completed actually, but it still has to be put out, we have actually succeeded in reconstructing the third kind of a future aim. We have actually accomplished in another project. We have actually succeeded in reconstructing a special kind of quench, which we call a Gaussian quench, which instantaneously takes a complex scalar field from this state with inverse temperature beta1 and chemical potential mu1 to another equilibrium state. And in this situation, we have succeeded in actually completely reconstructing the quench, which actually did this purely from field correlators across the quench. So, I mean, this is exactly in the flavor of the third point here. So, I mean, if it has worked here, then we hope that it can work here also. So summary is that just the motivation was that in this toy model, just calculate, motivation was that in this simple toy model, we wanted to calculate these HF heavy flavored meson in the inverted commas because it's a toy model. Number distributions at the final states for given heavy quark and light quark distributions in the pre-hadronization phase. And the strategy is to kind of model the hadronization, this instantaneous hadronization via quench superoperator Q, and then adopt an EFT approach to model this quench. And we have added terms to a certain degree, cubic, which I showed all the couplings, obeying general principles like hermeticity and trace preservation, and also abiding by certain symmetries, U1 color, U1 heavy, and U1 light. And ongoing is basically we are trying to calculate this perturbatively in the cubic couplings in scalar field theory. And the future is to kind of refine and relate this model to existing hadronization approaches like instantaneous coalescence And then also this interesting question of bootstrapping the quench, that can we reconstruct the quench couplings completely in terms of these cross-quench correlators, these meson light quark correlators. So if yes, then that too would be a probe into the QGP. And the second point is actually, I mean, it's reinforced by this second project which we have done, in which we have actually succeeded in completely classifying a Gaussian quench, albeit in a different context. But that is what I wanted to say. Thank you.
So thanks, Shridhar. The questions?
Very nice work. I find it very interesting. I have a very quick question on how do you help me understand this? How this zeta field in the final state, how that is a confining state? How can I say this is a heavy flavor meson?
Okay.
Instead of another fundamental field.
Yeah, I mean, it's just that it does not transform under UN color. It's a singlet.
Okay, it's a
this
singlet
we impose while adding these terms.
Okay, I have a follow-up question, but if anybody wants to ask, I can ask in the end. Okay, so what I can remember from these covalence or recombination models, while the fragmentation models is like it is a one single pattern is going and then you have shower of particles, so it's like a one to many process. But in recombination or covalence model, where basically what I can remember that they have this Wigner function for both of the patterns and they convolute and they do this thing. So there is actually it's a 2-to-1 process or 3-to-1 process covalence. So there was a question of how do you deal with the entropy, because it's a higher particle reduced to one lesser particle. But I find that the way you are building the setup, you can actually properly address this question how the entropy actually what happened to entropy by tracking the entropy throughout the process from the initial time. So it's a natural, I find it's a natural setup where you can actually properly address this question of entropy in recombination of coils.
Okay. Okay, maybe we can.
You want to answer? You want to comment on?
No, yeah, we'll try doing that. But I think there's been a recent paper in which they have modeled, I mean, I think it's by Fidel Tuagirayezu, recent paper, in which they have modeled hadronization as a quantum channel, as a super operator. And there they have looked at quantities like entanglement, entropy, and so on. Oh, just entropy, you're saying.
Yeah. Any particle fused into.
Yes, that's true.
Just question to you. So when people consider chemical freezer, then people already consider that in the original works they have this isentropic kind of a picture. They consider lines of constant entropy and then calculate the chemical freeze out lines. So when people talk about chemical freeze out in the context of hadronization, so then people consider it on lines of constant energy density or constant entropy density, right? So you are mentioning that those are implemented by hand, whereas this one can naturally.
Model became very successful, or people started thinking about those things because of this, because it was a natural model of hadronization that successfully explained the quark number scaling of V2, if you remember, like 25 years back. Why it was successful in giving this scaling? Because the sharing of energy, like two quark anti quark is moving, they are having meson, and then if it is having epsilon and this is also epsilon, together they have two epsilon, and then that was used to explain this quark number scaling of V2 eventually. So this is not possible in fragmentation. So equal sharing of energy between these two quark and anti-quark, or equal sharing of quarks in a baryon, one third, one third, one third. This is actually heart of explaining the scaling, quark number scaling of
Okay.
V2. So that was inherent in valence or recombination model, and it was kind of ad hoc. You have these two Wigner function placed together, you have a convolution integral, then you put by hand kind of delta function where you imposing this sharing. It's not like automatic.
Okay.
You are imposing that. So that's why I'm saying that there are things that have like that can be naturally explained probably here.
Okay, maybe that's very useful. Yeah.
Yeah, I had a similar comment or question of what he also mentioned. For example, if it is easy first to think of one pattern, how a color object converted into a colorless object. In that respect, in our field, jet side, we use string melting, how string melts into quark and diquark and thing. So is there any way to think of in that direction to impose your formalism such that?
Well, I'll have to think.
I mean, I don't know. I mean, I'm just asking to know whether
yeah, maybe I
that
haven't-
also makes sense, what you are saying.
Yeah, I'll have to think about it actually.
Yeah, because the coalescence and this fragmentation are two different regime in our
Okay.
field. So
But I had a question. You mentioned here one back levels.
Yes.
So this one is your like some barrier number. The context of CD do not have blind.
Yeah, I mean, this can be something like isospin.
How do you see that? Because you have this.
Because it only rotates the light. So.
today, Rishi's talk.
Yes.
So he was showing this energy correlated.
Yes.
If you were there.
Yes.
So there we saw that it's small delta R. We can perturbatively we can show that how hadrons are correlated, and that also related to your initial patterns hadronization pattern. But there is also another side which is called non-perturbative side.
So.
Yeah, so these are also very similar how the hadronization happen and when these patterns go.
Yeah, but here actually we'll be just doing perturbation theory. So I don't see how, because here we are just doing Feynman diagrams, and so I don't know how we'll get a handle.
Okay. Okay.
Then I don't see any further questions. So we thank Shridhar.
Okay. Thank you.